everyone, I'm Ashna. I'm finally a PhD student at the University of Sydney in Australia. And today I'm here to talk to you about basically the last 3 years of my research life. And I worked on, as Maria said, a huge range of radio transients. And hopefully by the end of this talk, I'll be able to turn all of you to synchrotron transients a little bit more. I thought I'd start with a little bit of a bio slide. No, okay. Yeah. You can keep talking. Well, I just thought I'd start with a bit of a bio slide. So this is me standing next to the Australian ASKAP Pathfinder, the Great Australian Outback. This is a telescope that I've worked with throughout my PhD, as well as the Australian Telescope Compact Array and a wide range of radio, optical, and X-ray telescopes around the world. My main research focus is synchrotron transients, with a deeper focus on gamma ray bursts and tidal disruption events, and I've also worked on novae a little bit. And I'm also part of the variables and slow transient survey with ASKAP, the Pan Radio GRB ASKAP follow-up team, and the Australian Centre of Excellence for Gravitational Wave Physics. Okay, so let's begin. What are synchrotron transients, right? Synchrotron transients are basically transients powered by explosive events, such as collapses or mergers. When these transients occur, they release relativistic or subrelativistic outflows, which when interact with their surrounding medium, they shock accelerate electrons to relativistic speeds, and this is what we see as synchrotron emission at radio wavelengths. Now, while radio emission mechanism stays the same for all synchrotron transients, the outflow energy and velocity can differ depending upon the progenitor, so we get all these a plethora of light curves basically. For instance, we get ultra-relativistic jets for gamma ray bursts, or more Newtonian spherical emission for supernovae. Now, we know what synchrotron transients are, but why are they interesting? Why do we care? Because they keep surprising us. Just when we think we know everything about jets and mergers, something new pops up. Now, I've just got a collection of things that I've basically touched upon in my short research career of 4 years. And for instance, GW7917, the first binary neutron star merger, was accompanied by the first kilonova and one of the first few structured jets. So then we went and started looking for kilonovae in relation to compact object mergers. And then we started finding kilonovae for non-GRBs or collapsars, which was a bit odd. And as I speak today, some supernovae are brightening somewhere, and we don't quite know why. I think the key point that I'm trying to drive with this slide is that all these discoveries were unexpected. Which is what makes synchrotron transients so powerful, because they're our window into the high energy astrophysics in the universe. Two of these anomalies that are quite close to my heart would be orphan afterglows and IMBH TDEs. So when GRBs are produced by collapsars, they interact with their surrounding medium to give us an electromagnetically evolving counterpart called the afterglow. Sometimes we only see the afterglow with no current detected GRB. This can happen in one of two cases. The emission is pointing away from us. We're pointing at the emission, but it's not looking towards us. Or the emission is pointing towards us, but we are just not looking in that direction. Up until now, there has been one convincing candidate in radio for this, and some other candidates as well. IMBH TDEs, so tidal disruption events are basically the disruption of stars when they get too close to black holes. The most well-studied ones have been near the supermassive black holes at galaxy centers. Recently, there have been ones that have been for black hole masses less than 10 to the 6 solar masses, solar mass, which is basically in the IMBH regime. And these have been found in the center of dwarf galaxies or in off-nuclear galaxy clusters. And there have been none detected in radio up until now. So going back 3 years, as I waited for binary neutron star mergers from LIGO Virgo, which was my initial project, following them up in radio, I started looking for off-axis afterglows that may have occurred from archival events in our survey data. So what I did was, we took 11 well-localized events, 10 binary black holes, 1 neutron star black hole, and we said, okay, let's look for any events that generated emission that might have occurred, but we didn't catch it promptly because it was probably not pointed towards us. But in daytime data, we could capture that afterglow, basically. So just on the plot up above here on the right, you see those localizations in relation to our ASKAP coverage. There are 100,000 sources in these localizations in racks, which is the Rapid ASKAP Continuum Survey. 1,000 were variable according to our criteria, and 4 that pass all filtering criteria for being an off-axis flow. Eventually, none were associated to the gravitational waves that we found them in. So we said, okay, we've got all this data, what can we still say about these events? Assuming that all these events were accompanied by jet emission, can we say that some basically a combination of energies, viewing angles, circumferential densities would have been detected with ASKAP, and if they could have been detected, could we basically rule them out because we did not detect them? So down here, I've got a plot for the same, basically it's a constraints plot, and what you see is we've got viewing angle on the x-axis and circumferential density on the y-axis, and you see there's an arrow pointing towards the region of bright afterglows that would have been detected with ASKAP, and we can rule it out because we did not. Now, like I said, we did not find any candidates that were associated with gravitational wave emission, but we did find one very interesting transient that I've now worked on for 2 years with telescopes around the world and people around the world, and we finally submitted it, and it's under review with ASKAP J. So this transient, it basically brightened by a factor of 20 in less than 250 days and has been declining detectably for over 1,000 days now. And here I've got the light curve for that transient. So the lighter colors here depict the higher frequencies, and the darker colors are the low frequencies. So you've got the ASKAP non-detections just there, and then this is the entire GMRT mirror-cat follow-up of that. This transient also has a peak spectrum. So we fit a smoothly broken power law to get out the peak flux, peak frequency, and the optically thin index. And we find that peak is at about 1 to 2 gigahertz, and the thin spectral index is about -0.9, which is very consistent with synchrotron emission. We also find that there is no rapid movement in the spectral peak. For those of you who do or have had any touch with GRBs, you know that the spectral peaks in synchrotron emission basically move up and down depending on the medium and the regime. But there was no rapid movement, so it was a little bit inconsistent with relativistic emission, and hopefully by the end that should clear up. So we've got a transient that turned off steeply, is declining extremely slowly with a peak spectrum, but no multi-wavelength counterparts, no gamma ray triggers, no optical transient trigger, no known HN or quasar along the line of sight, no infrared counterparts or X-ray detections, no circular polarization, no pulses whatsoever. This can allow us to rule out some transients, but not all of them, because telescopes are not looking everywhere all at once. We want them to, but they're not. This transient, interestingly, is offset from a low mass star forming galaxy at a redshift of 0.116. And on the right here, I've got a beautiful magical image of this region, basically. And you can see that galaxy with all the structure, and the cross marker shows the position of the transient. Using a mix of optical spectroscopy and imaging, we have determined that this is a UV bright, dusty galaxy surrounded by H2 regions, which can also be seen in the blobby structure around that main nucleus. There's also an emission excess of magical image at the position of the transient, which is very consistent with star formation, and it could be a nuclear star cluster. Now, the probability that this galaxy is just randomly sitting next to our transient is 1.87%, which means that it's very likely that this transient is associated to this galaxy rather than a wandering background AGN. Now, all this points towards this being evolving synchrotron emission from an extragalactic source. So let's try and compare this transient to the entire transient zoo, synchrotron transient zoo, and see what this could be. Now, here I've got the luminosity time plot with a number of synchrotron transients on there. We've got the GRBs in blue up top, the jetted TDEs in dark green. We've got the supernovae in gray and fast blue optical transients in pink. And our transient is basically these stars. The alpha launch date is unknown, so it's been shifted by the number of days according to the first radio detection. And just looking at the spot, you can say, okay, this looks very inconsistent with something less luminous like a supernova, or something even less luminous like an X-ray binary, radio bubble. It is consistent with a fast flow optical transient's luminosity, but fast flow optical transients, they decay quite fast and they complete their entire evolution in less than 1,000 days, where this is still detectable, still going. The luminosity evolution over time for this transient, if in that galaxy or if associated with that galaxy, seems to be very consistent, in fact, with the tail end of a jetted TDE or a GRB, just from the plot. So the TDEs and the GRBs. So early on, we took out some spectral parameters from our spectra, speed flux, speed frequency, and optically fit index. We can propagate that through a very standard equipartition analysis that is very common for synchrotron transients to get some outflow parameters, pending some assumptions, of course. And that's what I've done here. So we took out the radius, energy, velocity, the magnetic field, certain budget density, and the different colors are basically the different geometries. And I'm not going to be discussing each of these individually, but I'm going to compare them again to different synchrotron transients. So here I've got, again, energy velocity plot with the entire transient zoo, as well as our data points. So we've got the GRBs and the high energy high velocity space in blue. We've got the thermal TDEs and supernovae down the bottom here. The jet TDEs are just in dark green there. And our transient is just these stars. Red is the most collimated geometry, brown is the least collimated geometry. And again, looking at this, it is quite inconsistent with a supernova, a thermal TDE, or even AGN, which is just these purple triangles. And again, from an independent analysis, it is again pointing towards being in the mildly relativistic, non-relativistic outflow with high energy, very consistent with the Newtonian phase of a jetted TDE or GRB, or even a delayed TDE. How does the ambient density basically change with radius? Here I've got the electron density on the y-axis, the radius scaled by the Schwarzschild radius on the x-axis, and again, our data points here, red is the most collimated geometry, brown is the least collimated geometry, and that relation satisfies and r to the -2, which is again consistent with tidal disruption events or more wind-like media for GRBs. The density is consistent with GRBs, but it's lower than that found what's found for most TDEs, which is this entire population there. But this event is of nuclear, so that could have something to do with it. So in summary, everything points towards this transient being the Newtonian phase of a GRB or an off-nuclear jetted TDE, but is it physically plausible? Does it fit closure relations? Closure relations are basically mathematical expressions that link the spectral and temporal evolution for synchrotron emissions, quantum shock physics, and they basically depend on the medium, wind or ISM, or the regime, Newtonian or relativistic. So what the closure relations can give us is a temporal index. We extracted the spectral index from basically from the spectra. So what would the theoretical temporal index be? -2.4. Can we compare it to anything? Here on the right, I've got the flux, like the 9 GHz lag curve, scaled by the outflow launch date. We don't have one, so we have arbitrarily taken 1 day, 500, 1,000 days prior to first radio detection, and then we take out the temporal index. And this the calculated temporal index is very consistent with an outflow launch date between 1,000 days prior to the first radio detection. Early on, I also said something about the spectral peak evolution being really slow, but it is quite consistent in this regime, like the wind medium Newtonian regime. So it does fit closure relations. Now, there was an obvious lack of multi-wavelength counterpart. So can this be an off-axis jet that we're just viewing now because it's decelerated, will become Newtonian and come into our line of sight? To do that, we can use the Matsumoto and Fermi 2023 analysis, where they say that if there was something like this happening, then the Newtonian velocity for this quantity should be above a threshold of 0.23. And I've calculated that for all our ASKAP epochs. And all our assumed collimated geometries are basically sitting above that threshold. So it is very possible that this could be an initial weak off-axis jet that we're just viewing now. In conclusion, we found a rare radio synchrotron transient with ASKAP, which is either the second most convincing orphan afterglow discovered in radio, or the first radio discovered INBH TDE. I would also just like to quickly highlight two other things that I've worked on. So just classical novae, a targeted search to the ASKAP pilot survey, which is my honors project, and I'm currently working on some GRB modeling, which happens to be consistent with a two-component jet with a hard electron index. Oh, and of course, I completely forgot. I'm looking for postdocs, postdoc opportunities next year. And so please reach out. I'm sitting in room 124, James' room. So if you want to chat about anything, anything jumped out to you, please come chat to me, and I'll just leave it there and take any questions.
How well constrained are the epsilon E and epsilon V parameters at this point for transients like this?
For the interesting transients, well, we have in
Transients.
general, I think, yeah, in general. Oh, I mean, we have taken, so if you look at these plots, I don't know what is, okay, so if you look at these plots, right, so if you look at the errors, that's all the epsilon E, epsilon V that are known basically for all synchrotron supernovae, TDE, GRBs. So I've taken all of them and I've put them as like giant error bars on these values. So they're all included in there, even here. So it's basically the entire combination that I've taken and put them.
So, I mean, it looks like it's making about an order of magnitude difference.
Yep.
And is that range constrained from some evidence, or is it just a ballpark?
No, it's just, because we don't quite know what this transient is, and this is like an attempt to classify it, this is just a broad, this is what we think it is, and we've not done any like further modeling to kind of test, okay, this is what we like fitting. I think that would be part two of the paper series.
Is there any hope of finding out maybe from VLBI, but I don't know if this largest radii, I'm not good in thinking of Schwarzschild radii of black holes, but this is in physical units, so is there a hope that you can resolve it or not?
Well, thanks for that question, because our LBA data is currently somewhere in the Great Australian Outback, traveling through trucks to get to the location that we needed to. So I think that's why I say that I don't have enough time left on my PhD to kind of incorporate that in this paper, but we will be writing another paper once that data comes in, which will give us a very good understanding of the radius again, and as well as other factors, and we can do a second observation to get the velocity and everything.
So you should be able to resolve it, you think?
Yes, yes. Although at this late stage, we won't be able to distinguish between the TDE and the GRB scenario. That's the only downside, because if it's really a Newtonian, if it's really a Newtonian outflow, we can't say anything. Yeah. Although that just we could have distinguished between TDEs and GRBs if we could probe the UV like disk at late times, but this is a UV bright galaxy, which kind of just it's unfortunate. Yeah.
So what was the threshold?
0.1. Yes, Peter.
How would you get an off nuclear TDE?
From an INBH. I mean, like, I think.
So is the implication that there's an intermediate mass black hole sitting under there?
Yeah, because in the Magellan image, I mean, you can't see it quite here, I've got it in my paper, a better plot of this region, but when you model out all these circular components, there's still emission excess at the region of the transient, which could be a nuclear star cluster offset from the galaxy. Yeah, that's kind of why we think it could be a TDE.
I guess completely Just from the fact that GRBs occur in this kind of galaxies, that seems a little bit more plausible. perhaps.
Yes. Yes, it's just that, you know, when you can't rule out.
Yeah,
something,
no, it's good to keep an open mind, for sure.
I mean, I'd be happy this is wrong enough to know you could submit to nature, I could do that.
Thank you.
Okay, awesome, thank you.
It's